Hello everyone. So in the previous video we talked about the different methods that we use in order to determine the molecular weights. So I talked about certain absolute methods, relative methods and fractionation methods. Some of the methods you might be understanding by their name. Some might be new or not very familiar to you. But since in your course we do not have to study the details of each of these methodology for determining the molecular weight, so I'm not intending to do that in this particular series of lectures. So therefore, uh, for your understanding, you just have to just remember that we have these techniques available for determining the molecular weights of the different polymers. Okay, so in this lecture, I would like to concentrate on the various formulae that we use in order to calculate the molecular weight. So basically, an important thing that here I would like to introduce is the concept of average molecular weight. Now, this kind of use of terminology might be very new to you because you have only talked about the molecular weight. Now, here we are introducing average concept because as we know from our previous understanding about the molecular weights of polymer that we do not have a very uniform distribution of molecular weight when it comes to a polymer sample. Usually the polymer samples are polydispersed in nature, and therefore we have to introduce this concept of average molecular weight. So whatever I'll be discussing different types of molecular weights, like some of the terms you might have heard, like number average, weight average, okay, Z average, viscosity average. So we have different types of average molecular weight that we use in order to determine the molecular weights of polymers. So depending upon the technique that we use to determine the molecular weight, we have different average molecular weight that comes into existence. Okay, so let's talk about the number average molecular weight. So here the formula that uses to determine the number average molecular weight is nothing but summation Ni upon summation Ni, where Ni is the number of molecules or number of moles of that molecules having a molecular weight of Mi. Okay, so whenever we use techniques like colligative property or N group analysis to determine the molecular weight of polymer, the molecular weight that we obtain using that particular technique is the number average molecular weight. So this is the basic formula that we use in order to determine the number average molecular weight. Okay. Now, another different type of average molecular weight that we use is the weight average molecular weight, represented by this particular formulae. Okay, and it is nothing but equals to summation Wi Mi upon summation Wi, where Wi is the weight of the molecules having a molecular weight of Mi. Now here I would like to again reiterate this point. Now in the first case, when we talk about the number average molecular weight, we are actually talking about the number of molecules having a particular molecular weight. So as I told you, it's a polydispersed sample. So we have different types of molecular weight, like let's say M1, M2, M3 molecular weights of different molecular weights in the polymer sample. So if suppose M1 molecular weight, how many moles of N1 molecular weights are present there, that is what is represented by this particular number of molecules or number of moles in this particular expression. Okay, so similarly when we talk about the weight we are not talking in terms of moles or molecules. We are talking about the weight of that particular fraction having a particular molecular weight. Okay, so this is the basic formula. Then we know that we can write Wi as Ni times Mi, because why? Because we know that the number of moles we can easily obtain simply by use, because we know that the number of moles you can easily calculate by the formula Wi upon the corresponding molecular weight. So from that, Wi can be written as Ni times Mi, and that's why you have this particular formula also, which can be used to calculate the molecular weights in here. Okay. So if we use the light scattering experiment, the molecular weight, the average molecular weight that we calculate is usually the weight average molecular weight. Now here is some of the example that is given here. So if we talk about the 9 moles of a particular molecular weight, please ignore these representation is wrongly written here. So we have a polymer sample in which 9 moles have molecular weight 30,000. 5 moles of a particular polymer in that polymer sample has a molecular weight of 50,000. So if we are asked to calculate the number average molecular weights, we know that it is nothing but summation. We know the formula, right? So the formula says, let me write that for you. So formula says summation Ni, okay, Mi upon summation Ni. Okay, so that is why we have two values of n here, n1, n2. Let me write it as n1, and this is n2. So correspondingly we have m1, and this is m2. Okay, so we can put the values in this formula, and we get the value as 37,000 gram per mole. Similarly, when it comes to Wi, we will use that extended formula, that is Ni Mi square divided by summation Ni Mi. Okay, so that is what we have done here, and we got the value as 40,000 gram per mole. Let us look at another aspect. So if suppose we have weight value given here. So here we are given the weight. So we have W1 with molecular weight of 30,000, W2, that is weight of the polymer with molecular weight 50,000, is 5 gram. Okay, so we know that we can easily calculate the weight average molecular weight simply using the formula Wi Mi upon summation Wi. So that is what is used in this particular formula, and we got the value as 37,000. Now how to get the number average molecular weight? It is also very simple. We know the number average molecular weight is nothing but Ni times Mi, Mi upon the summation Ni. Okay, so Ni we know we can write it as nothing but Wi upon Mi. So into Mi. Okay, so we know that this will cancel out. So we are only left with Wi, summation Wi in the numerator. In the denominator you have Ni, which again can be written as Wi by Mi. Okay, so if we see the simplified formula, it is nothing but in the numerator we have summation of Wi, so that is what is done here, divided by the summation of the fraction Wi by Mi. Okay, so that is what is done here, and we got the value as 35,000. So apart from that, we have another average molecular weight, which is called as Z average molecular weight represented by mz. Pardon me, here we have a bar over it, okay, to represent the average, okay. So that is nothing but equals to summation wi mi square upon wi mi, okay. Again you can write wi as ni mi, so you can have another formula, summation ni mi cube upon summation ni mi square. All these terms have similar meaning as we dealt in the number average and the weight average. So if we use a technique called ultracentrifugation to determine the molecular weight, what we obtain is a Z average molecular weight. So this particular equation is the general equation which we can write as mz equals summation ni mi a to the a plus 1 upon summation ni mi a. Okay, so when a value is 0, this equation reduces to the number average molecular weight. When a value is 1, it reduces to your weight average molecular weight. When a is 2, it comes to the Z average molecular weight. So in terms of this particular way of writing the three mz, mw and mn, we find that mn is the lowest value, then we have the mw, then we have the mz, because mz we have the cube, mw we have the square, mn is simply ni times mi. So the numerator value is highest in the mz, then little lower in the mw, and then we have the number average molecular weight. So this is the like the value, like which is the bigger value, you can easily understand or come to the conclusion from these formulae. Now one more type of average molecular weight that you need to know is the viscosity average molecular weight. So it's written like this, and it's having this particular formula where A is a kind of variable. It is different from the A that we have used previously to represent the general formula. It's formula, it's in this particular formula, it's just a variable whose values vary between 0.5 to 0.8 for most common polymers. However, for rod-like polymers, A will have a value of 1. So in that case, when A becomes equal to 1, the equation reduces to that formula of the weight average molecular weight, and that's why when A is 1, especially for the rod-like extended polymers, the viscosity average molecular weights equals the weight average molecular weight. Now the A value in this particular equation actually comes from this equation called the Markov-Sakurada equation. Okay, this is the equation that we use in order in this particular viscosity for determining the viscosity average molecular weight. So this equation, if we take the log, it comes like this. Okay, so when we plot a graph, okay, between the y, that is the log of eta is the viscosity here, versus the log of mw, which is your x-axis. Okay, the slope of the graph will give the value of A. So when we use the relative method, that is the viscosity of the solution, okay, we use basically this equation to calculate the slope of the graph to know the value of A, and from that we can easily calculate the viscosity average molecular weight. So we do not have that graph plotting in your course, so we are not doing that, but you should understand this particular formula, and you should know what its terms means. Okay, so in the next class I'll deal with some more aspects of this molecular weights. Thank you.